In line with the Z-bit algorithm, what we have dealt in the earlier discussions, where is the need of that? Because we haven't seen the need of Z-bus for our studies. We understood how Z-build algorithm works for modification of a branch, modification for the link, and how system Z-bus is updated for the further requirement was just witnessed. Now we will see where is that need of Z-bus for the real study of the power system. That is called algorithm for short circuit computation as a basic heading. For this, let us take a n-bus system. Here, this n-bus system, a power system is just put with a oval shape. There are so many buses where we have generators and other interconnections. It has been given. So n buses and the pre-fault voltages. When this system is healthy, n bus system is healthy, delivering the requirement of the power system and balancing the P and Q, then system is a normal condition. That's also called as a pre-fault or initial condition. So all the voltages of bus 1, bus 2, bus 3, bus n during pre-fault or during the normal conditions were written as V bus 0 initial condition. It means V1 0, V2 0, dot dot n bus 0. This is called a vector of initial voltages of the system before the fault or preconditions. Let us assume there could be a fault in any one of the bus. If there is a fault in any one of the bus, the particular generator path just taken a fault, rather than injecting a current to the grid, it will start flowing to the ground. If there is a line to ground fault, heavy short triple line to ground fault, that there is a short circuit, definitely current, suppose say R bus only, current start flowing down to earth. In that regard, what will be the voltage of bus 1, bus 2, bus 3, bus n during the fault? That's called V bus during fault, V bus F. You can see here, V bus 0 means before the study of power system faults or anything, what is the initial voltage of the buses? That is V1 0, V2 0, Vn 0, like that. When there occur a certain fault on the given power system, definitely the voltages of all those buses which we have seen, V1 0, V2 0, Vn 0, won't remain same. There will be a change in voltage in all those buses. That is given as V bus F equal to V bus initial plus delta V. This delta V is the differential voltage with the V bus of that particular numbered bus from the references or from the initial condition. This delta V is nothing but differential vector of the voltage, which will be the deciding factor to give us bus voltage during fault. Then let us consider a fault on bus number R, which is there. Let us assume rth bus is faulted with the fault impedance ZF. The post-fault voltage vector, nothing but once the fault is occurred, what is that prevailing voltage on all the buses of a given power system? We call it as post-fault prevailing voltages are given by vector of delta V, which changes the voltage of the initial value V bus 0. That's what I can say. This is the initial bus voltage. This is the initial bus voltage and a vector of differentials to respect to voltages, which will make voltage of that bus after the occurrence of the fault. Let's see next step 3. This particular representation of the power system for the fault study is such a way done is drawn Thevenin's equivalent reactances. We all know when you want to reduce during across the points of fault, entire circuit is to be reduced. Then we use the Thevenin's representation and short circuit those voltage sources, open circuit those current sources, leave the dependent source as it is, and represent VOC and ZTH of that particular network. How we do Thevenin's representation? Similarly, Thevenin's representation is done for Gen 1, Gen 2, Gen 3, Gen N, and Gen R with X dash dr, X dash dn, X dash d1. What is transient reactance behind the source? transient if it is author has given transient, or trap transient, whichever is given, that generator is represented by x dash d1, x dash d2 at bus 2 like that. And bus R is having a fault with the fault impedance ZF, which is having a current injection to the loads, fault side by an IF value. Then this is represented by this symbolic representation. Therefore, now I have what is this mismatch vector, residue vector delta V, which will definitely change the values of initial voltage vector V0 bus, that is Z bus into vector of fault currents. So now we got to know in the form of a matrix, delta V is a delta V1, delta V2, delta V, like that. This is having a column vector, a column of delta V1, delta V2, like that. And JF, fault vector of current, that's also having Z1, Z2, Z3, like that. And it is multiplied by Z bus of the system. Now here comes Z bus of a system to compute post-fault voltages of a given power system. Now you got to know here, whatever the study we have done, formation of Z bus by building algorithm, scratch, element by element addition, either in the form of a branch or in the form of a link, so that such an activity constitute Z bus of a given power system in steps. So that was an activity we have already learnt. That is useful over here to understand the post-fault voltages of a given power system for the analysis point of view. Here we are trying to analyze short circuit study. Short circuit would be a massive impact like a transient and others. So for that, Z bus is very necessary. So that has created the point now, Z bus of a system is very necessary. Then how Z bus of a system is given? If I have n buses in the system, it's a n cross n dimension. Z11, you can see the first row, Z12, second element, 1n. So called Zn1 to Zn. So you have n rows, n columns, n cross n matrix. So this is the system impedance matrix. This is used to compute mismatches or residues delta V's with the current which is flowing to the fault. So therefore, as per the requirement for study, draw the system Thevenin's equivalent of a system using the transient or subtransient reactances given by the problem. Then obtain the Z bus and take the particular vector of current, which is the current which is a fault current going to the point of fault, then get the value of delta. Then it is written here in next step. Now we excite passive Thevenin network with the VR in series with the ZF dash, because there is a fault occurring here. To create IF current, there should be a creation of VR0 in series with ZF, which the vector delta V comprises of the bus voltage network. Now this current vector, there are currents in I1, in bus 1, bus 2, bus 3, bus N, bus R. Now there is a fault in Rth bus. You will find JF, you can see here, JF is a vector of currents, 0, 0, 0, 0, 0. Only the Rth bus voltage, IR, which is faulted with the ground, IR fault equal to minus IF, is a going out current. So this is becoming a vector of current where which bus is encountering a fault, only that element is non-zero. Rest all are zeros, because I am analyzing specifically a fault on Rth bus only. Then I will be knowing what is that current flowing. Then only that element is non-zero. Then using this, I can write delta V and Z bus of a n bus system I know. Then JF, it could be IF also. Some book refer, this is referred in Nagarth Kothari references. JF is a vector of current in which only the Rth bus is encountering a fault. Therefore, current is going out of the bus, it is a minus IF. Now, if I multiply this Z bus with JF, I'll be able to get differential voltages delta V's. For me, what is that Rth bus voltage is interesting. When I have V1, V2, V3, V4, V5, V6 pre-fault, which were like this. And after the occurrence of fault, V bus F, V bus 0 plus delta V. Then I am in need of calculation of delta V's. Once I know the delta V, I can take up that V bus initial with which definitely give me the post-fault voltages of the given system. Then I am working upon this. For that, delta VR equal to, when I take this product, this vector with this is a column vector, which is this vector. This is the dimension of a matrix n cross n. When I take rth row multiplied with the column, only the here I have row number r 1 1 2 1 3 1 r1 k1 m1 n1. I get rth row. When I multiply with this column, nothing but z bus rth row and a current vector, when I multiply, I'll be getting delta VR. Like this, delta V become delta V1, delta V2, delta V3, and delta VR for the rth bus. Just imagine this is a vector, like a column vector of a voltage. This is a Z bus of n cross n. This JF is a vector of current like this. The rth row equation, one of the independent, there are n equation definitely when I split this into simpler equation. I am interested to know about equation number R of the bus R. Then it is, I can write delta VR. From this, one of the delta VR, I pick it out. Delta VR equal to the row which I take out and multiply with the column. Already these are these zeros. This will produce a zero. What is non-zero? Only rth element. In the rth row, r cross r. R cross r is ZRR element. Can you see here? ZRR into minus of IF provide me the differential voltage delta VR at the bus number R. Then what exactly I calculated? During the fault, if there occur a change in voltage, what will be the prevailing voltage after the occurrence of the fault, post fault? That is delta V's I should find out. For an arbitrary fault on an rth bus, delta VR, which stand as minus ZRR into IF. Then using this delta VR, I can compute the post fault voltage V bus during fault or occurrence of the fault, like that. So for that we can just see. Next step. Then VR after the occurrence of fault is VR initial. Its initial voltage. Then the residue what I am able to calculate, that provide me VR initial minus ZRR IF. But we know this is the voltage prevailing existing after the occurrence of a fault. This is one way of computation from previous initial estimate or initial values. Once there occur a fault, difference in voltages as a mismatch vector, initial vector, when I take a summation or its integration into a value, that lead me VRF, nothing but it's a revised value. It is also equal to, from this bus perspective, if you stand with this bus and say, what is this? VRF, voltage of rth bus during fault is IF into ZF. This is going through a fault impedance of ZF. ZF into IF is VR during the fault. Therefore, these two equations must be one and the same, because this is also VRF from initial voltage and differential vector, and this is the actual voltage of rth bus during the fault, which is ZF into IF, which I can write by equating. Therefore, ZF into IF equal to VR initial minus ZRR IF. From this, I can take out IF as a heading of the equation. You can see here what I am doing. I am taking this ZRR to the LHS side. I take out IF common. When I take IF common, ZF plus ZRR become the coefficient here. That I'll push to the denominator. That become IF equal to VR initial divided by ZRR plus Z fault, impedance with which fault is likely occurred. Therefore, this is with respect to current at fault current at rth bus situation. Now, what will be the similar change in the voltage? Like VRF, nothing but it is a post fault voltage at bus number R. Similarly, what is happening at bus 1? Post fault voltage at bus 1, bus 2, bus 3, bus K, bus M, bus N. I don't know, but I can write. Therefore, for ith bus, what would happen? For any bus, ith bus, delta Vi, like a delta Vr, one of the possible rth row of the delta V column vector, I picked it up. Likewise, delta Vi is one of the possible occurrence of a delta V is being done. Delta Vi is equal to similarly minus Z I R I F. What is this? Very interesting here. Now this ZIR, you are on a ith row. You are on a rth column. Column number R is fixed. Row is changing. Row number 1, 1R. Row number 2, 2R. Row number 3, 3R. Then like that, ith bus IR. M bus MR. Nth bus NR. So this I is anything like that. So therefore, I in general we can say delta Vi equal to minus Z I R I F. This will give differentials to the particular initial voltages. Wherein now I can write invariably any bus voltage after the fault if VIF, if I call VI voltage of ith bus after the occurrence of fault VIF equal to VI0, its initial voltage, minus this term ZIR IF. So I am trying to make it generalize as an ith bus where I is 1 to n. Okay, it can be R also. So therefore, this is the voltage noticed at ith bus. So therefore, substituting in this equation, IF is there. IF we got already. When there occur a fault on rth bus, the fault current IF is given by VR0 divided by ZRR plus ZF in the denominator. This value stood as a current magnitude. This magnitude of current I replace in this position IF. Therefore, I will be getting VIF, voltage at ith bus after the occurrence of fault is equal to voltage at that bus initially minus, you can see ZIR into whole term here, V0R divided by ZRR plus ZF. So I am just substituting IF in this case. Now this is the voltage at all the buses I stand 1 to n number. So initial voltage minus the ratio of the impedances connected to that fault and considered bus. I am considering ith bus. Rth bus is encountering a fault. IR is my link. Right? You can see here. Ith bus post fault, after the occurrence of fault, what is the effect of that fault on a rth bus on a ith bus? VIF. Ith bus post fault voltage after having experiencing a fault, what is the voltage available here is equal to Vi0, its initial voltage, minus the connecting impedance between the bus I and R represented in the Z bus, ZIR, divided by diagonal element of the rth bus RR plus ZF, with what it is getting faulted into VR. So therefore, this stand as one revision of calculation of VIF. Again, I can simplify. A case study may occur. Bus number I may be R itself. I replace a special case study. I can be R. If that is the case, what will happen? It become VRF. VRF equal to VR0 minus ZIR, ZRR, ZF, VR0. Then if I take this LCM, ZRR plus ZF into VI, now that has become already VR in the next step for I equal to R. Definitely I will have sum of the terms cancellation. This I became R. So you will find, just observe this equation. Z, when I equal to R, I become R. It becomes ZRR into VR0. Here comes VR0 into ZRR. One is plus, one is minus. So ZRR, RR cancels off. What remains is only ZF. ZF only remain the numerator. Then ZF into VR0 divided by ZRR plus ZF. This is called post fault at rth bus after the occurrence of a fault with the impedance ZF, whose initial voltage VR0 is known. Now we can imagine this scenario. There is a fault in the system which KLIT is interacting with all the department as a buses. What is the healthy situation What is the healthy voltage situation of all the department? Bus CS, bus EC, bus IS, bus EE, bus MEC, MES, bus civil. Like that, you imagine office. All the bus voltages are pre-fault voltages. Initial voltages are known to you. Once there occur a fault in the library department bus, will it not going to affect the voltages of all the buses? Surely it is going to affect. Once that affect, that's called post fault voltage measurement at all the buses whenever a fault is encountered in the system. Therefore, this is going to help. This may be this may be VI voltage after the fault at electrical department is equal to electrical department initial voltage and its connectivity with the fault at library method or maybe library for me. Likewise, I can compute and I can simulate this requirement. So therefore, here comes ZIR, ZRR, ZF like that. These are truly taken from Z bus of a given power system. There comes a necessity that Z bus is to be framed. Once I am able to connect this standard equation for I equal to R, it's so simple. There occur a fault on rth bus voltage only. Voltage of a library bus, when there occur a fault on library itself, it is VRF. After the occurrence of a fault, whether there will be a voltage measured or not, which is VRF equal to ZF or ZRR plus ZF into VR initial. This way, very simple, it flows outline. Then, as said, so if we, whatever the voltages initial, which I go back and tell you, this initial voltages which I was speaking, these are very necessary. Suppose these are to be, where do we get these things? If there is a question, they are taken from load flow study. Load flow study require basic assumption. That's what is being written here. As said, relationship VI zeros are the pre-fault bus voltages assumed to be known from the load flow study. When you want to study a short circuit study or any transient study applications due to faults or due to any disasters, what will be the prevailing voltage after the encounterance of such a fault? After the encounterance of such a fault. Therefore, that is called post-fault. After the elapse or occurrence of the fault. Therefore, for that pre-fault information very necessary. Without the pre-fault notices, I cannot compute the post-fault things easily. Therefore, they are well known during their normal working condition before it encounters a fault. That is done by load flow study. So V's are known. Then Z bus matrix of a Z bus matrix for the short circuit study need to be obtained either by inversion of the existing Y bus. We know that inversion of Y bus which is in a singular transformation method. In case of singular transformation method, one of the bus is considered as a reference and total bus dimension become one less to the total count existing in the system. So that bus and a Z bus what we build from the scratch are just opposite to each other. That is in admittance domain. Z bus what we are talking is in impedance domain. If I have Y bus of that notation, invert it, it becomes Z bus of your requirement. If you know the Z bus, invert it, it becomes Y bus. Likewise, I may get Z bus from building technique, or if I have a Y bus available, invert it and get the Z bus for short circuit study. Now you are coming to know all the way we have learned admittance, Y bus by inspection, Y bus by singular or mutual, without mutual, and incorporation of transformer. Everything I discussed in admittance only. But when I perform such experiment in laboratory, you might be aware, I was entering resistance and reactance and impedances only. There comes the study, real study require impedances to compute its real impact on the computation. Therefore, it must be seen carefully. Z bus is very important like a Y bus for our short circuit studies. Very basically, whenever you perform a short circuit study, preparedness, time setting of circuit breaker, trip merging, whatever kind of protection mechanism and fault related work when you work into, for that to work, you require a Z bus of the system. So that's what I'm trying to highlight. So therefore, you need to get either building by Z bus algorithm or by inversion. Once it be ready. Now, once it is ready, we can definitely say line flows. As you are aware, simple power flow concept we have studied. Between two buses, whenever I and J are connected by a YIJ, VI, VJ are being the voltages, then I can definitely write current that can flow during the fault from bus Vi to bus J can be Yij into Vi fault minus Vj fault. During the occurrence of a fault, what is the prevailing voltage of bus I, Vi, prevailing voltage of bus J, Vj, and difference in potentials reason for the flow of current, which would matter Vi of F minus Vi of J into Yij. That give me current that can flow from ith bus to jth bus. Likewise, we need to calculate the post-fault generator current and load flow or pre-fault generator output P equal to PGI plus JQGI like that. Now, a simple representation is being done. A synchronous machine is represented as transient reactance and a source behind that. Then EGI, transient, one single dash is there. EGI, XGI, and it is ready to inject IGI initial condition. And potential what can maintain at the ith bus is Vi0. Pre-fault means during normal operation, Vi0 was the voltage noticed at ith bus, Vi0, and that whole mechanism is represented by uh, uh, equivalent voltage source and reactance in series with which is subtransient reactance X dash GI EGI internal voltage. So this is how we can do. Then similarly, it's given during the fault. During the fault, EGI dash, you can just see here X dash GI and IGI F. Here IGI 0 is the initial condition before the occurrence of fault. Once there occur a fault, definitely the magnitudes of calculation will change. But how we can represent it? Vi during fault. This is Vi during initial stage. Vi during fault is IGIF. That's all. Now we know what is this current injected by this to bus I. If I know its power rating, the generator's power rating PGI, QGI, PGI minus JQGI divided by VI gives me initial inject of current. That's called pre-fault generator current, and pre-fault output voltage would be PGI plus JQDI. Means JQGI. There is no load here, only injections. PGI plus JQGI. Then this E dash GI written from VI. VI plus J into XGI dash IGI0 from KVL, knowing the VI receiving end, getting the voltage of sending end. Okay. E dash GI equal to VI plus JX dash GI I0 GI. From the short circuit study, this is internal voltage computation. From the short circuit study, any bus voltage, ith bus voltage after the fault is obtained. Then this is rewritten as, from this perspective, IF GI, current injected during the fault, IGIF equal to E dash GI minus VI divided by J times X dash G. It's very simple, isn't it? This representation I am doing. IGIF is E dash GI minus VIF divided by J X dash X. Similarly, I go ahead. So this necessitated the need for study of JUT. This was one simple concept I wanted to convey you. This is how a short circuit theory, short circuit algorithm, we call it as. How it is done, I just repeat back. The first step is entire system you represent, find out what is that equation you need to obtain, then draw the Thevenin's equivalent diagram without the sources, then obtain Z bus, then get the value of voltage of VR0, then delta VR, then respective equation equality VIF, how it is being done. So it is being done for I equal to R, special case study. Then it comes to Yij, straightforward here itself. I'll show back. From this page number 1, 2, 3, 4. There are 4 slides which I am showing you. From these slides, what would be the question? Explain the algorithm for short circuit computation would be the question. For that, one rough sketch, these two vector representation in just 1 or 2 line, a text connect diagram with this equation, 1 line or 2 line, then directly move with this block, how it is represented, how is that Z bus into IF constitute your VR or delta VRs. Then comes one of the bus voltage you consider VR, which is a fault voltage, fault bus or a faulty bus for the study. Then equate those two equation of VRF through relativeness or by exact value. Then get the gist of it.